Boo-boo, Calculus BC. I'm doing this video to rip off Khan Academy's explanation of sigma notation. Sorry, Khan. If you don't want to watch my video, go watch his. They're good. So, sigma notation, summation notation, same thing. I say sigma, two syllables, easier to say. And that's what the symbol looks like. The basics are outlined here pretty nicely. So you have usually like n equals 1. Sometimes n, sometimes I. It's our counting number right here. It's kind of like x, but usually we don't put x for these because that represents a different. You'll see later in BC because they just mess things up. N's pretty common. So we have the expression right here. And then this is like what you start at, and this is the number you finish at. So if I said, and the sigma's idea is like sigma means sum. You're summing all these numbers, and it's a sequence of numbers. So the first number is when you plug in n equals 1. So it would be 2 times 1 minus 1, or would be 1, right? 2 times 1 minus 1. And the next number would be 2 times 2 minus 1. And then the third number, when you plug in 3, would be 2 times 3 minus 1. So you plug that in, this would be 3, and then this would be 5. So the idea is you're adding these three numbers up, and then your answer to this would be 8. So this is equal to 9 at 8. That's what you're doing with this kind of stuff. Sigma notation. Again, this is your starting number. This is your finishing number. This is like the expression, the formula that you're plugging it into. So if you know all that, that's the first step to sigma notation. All right. So, oh, look, I just did it, and then he did it all down here. So if I had this problem right here, and you had to do this, n squared, you'd go with 1 squared, and you go 1 to 4. So plus 2 squared, plus 3 squared, plus 4 squared. So it'd be 1 plus 4, plus 9, plus 16. Oh, or which one of these? It'd be B. Oh, I'm so smart. Great. That's what you're doing. You're adding them up. For sequences, sometimes if you've done sequences in series, you might have seen this before. Yeah, you could, like, they could have different letters in here, like K. All right. K, you can still handle that. I don't think I need to do more of those. You can try them out yourself. Oh, so sometimes, hey, I might mix up variables in here. So this will be later in BC, like we have n's, but we also have x's or something like that. So we're only plugging in for the n and not the k. So if you were trying to do the sigma notation, it'd be, 1 plus k over 1 plus 1, k over 2 plus 1, etc. And it would actually come out to this. So you don't necessarily sub for every variable if they throw that trick at you. And that might be relevant later in BC. Okay. So same thing with, so there's your example. All right. So that's that first part. That's how sigma notation works. Basics. All right. So, but this, we're not even at calculus next. That's like pre-calculus stuff. Did Salcon really do that? A hit and run in 2012 or 2002? Time to cancel. I'm glad he didn't have Twitter then. Time to cancel him. I haven't done that. You know who else hasn't? John Smith subs. You go here. You feel safe. Wait, say that again? Oh, we don't. He might have. But it's in Miami. Oh, Florida keeps good police records. So you could look that up. I don't want to search him up. But I don't believe so. How could someone make such delicious subs and do anything wrong? No. Yeah. All right. Get back to real stuff, calculus. So what's the point of this sigma notation for calculus and for the AP test? This kind of stuff used to not be in the AP test too. They just added this like in 2017. Like when I first started teaching this. I mean, it was always there, but it was like never on the AP like this. So the idea is that, hey, we've done Riemann sums last time. We were adding up a bunch of rectangles, but left and right and whatever. But we can represent if those adding up the Riemann sums in sigma notation. Like especially if you're taking a case like this, like a Riemann sum, like this area under the curve, and let's say that the width of every rectangle is the same. So so in the case where like the width of every rectangle is like 0.5, so these are all rectangles right here. And let's say you're doing this as a left hand. And yeah, I could plug all those heights in and add them in, and do the sequence of numbers of adding up the areas of all those rectangles. But I can also represent that in sigma note. Doesn't follow. Wouldn't it be great if I could just mark up? Or okay, they did it right here, right? But and I could represent adding all those up. So let's say, oh, the area of this so they chose a 1.5, right? So it'd be like the first one's 1.5 times whatever this height is. Oh, it's so gross. I don't even want to figure it out. And then they say, hey, you're just adding up the area of each of these rectangles separately, base times height. But you could also represent this in sigma notation. Okay. So if you had 4 rectangles, I is 1 through 4. You don't always, now all our examples, you start with 1. You don't always start with 1. You can start with any number. Typically it's 1 or 0 in a lot of cases, but watch that trap. So it's just a different way of representing those rectangles and Riemann sums. So I don't know why they're doing this. Okay, so they're like blah blah blah. If the width are all the same, then you could just have the formula for the height is just that square root times like the change in the x. And so you're going to see sigma notation like this. So let's say I had the change in the x was 0.75 on each of those. And it's so they could represent, and this is just the square root of x function. And you're starting at 0.5, and then you add, so every time you do a new rectangle, like this one's going to be at 1.25 times 0.75. The next one would be at, or the square root of 1.25 times 0.75. The next one's going to be the square root of, what's that, 4. No, square root of, I don't even know what that is. Whatever that is. I'm getting distracted. Basically, they're saying, hey, I could take that formula and write it as a Riemann sum. It looked like this. This is going to be the width of the rectangles. If I was writing these as sigma notation, this is going to be my width, the delta x. And then this is going to be related to my formula. So you know how the formula is y equals square root of x? So it's not x underneath. It's going to be like based off of where you're starting, plus you're adding that width every time. So this is kind of like the width right there. So your delta x, how much you change, or the width of every rectangle. And this is kind of like your y equals whatever formula square root of x, but it's based off of where you're starting with x, starting with your integration, and the width of every rectangle. Does that have to make sense? We'll see what you actually have to do, right? Oh, and then they start explaining these in notations like this, delta x and your function, kind of like what I just said. All right. So what are the types of problems they might ask you? So if I said this, I have this function that's this, and then it's going from 2 to 7 using left-hand Riemann sum with 10 equal subdivisions. What's the length of each rectangle? Well, if you know it's equal, you got to figure out this whole length here. That length is 5. And then you got to chop it up into 10. You go 5 divided by 10. And then I'm just going to say 0.5. Am I right? Next question. I think I was right. Okay, so the idea is you're dividing it up. Oh, yeah. What's the expression to the right? I don't want to even bother with that. Hopefully we don't have to do that. I don't think that's important. All right, this is where it is important. This is the kind of stuff you might see on an AP test. So which one of these would match up to the correct expression right here, right? So I'm going to write some information. This is the kind of stuff that I've seen. So you have 9 equals, you have this function right here. It's going to be 5 over x plus 2. And then we have 9 subdivisions. We're going from 1 to 7. So our length is 6. Say my length is 6. We got 6 divided by 9. My delta x right there is going to be 6 divided by 9, or 2/3. So I'm looking for something that has a width of 2/3. So if I'm looking at my choices here, I know it's got to be C or D, because that's the width of the rectangle, not A or B. And which one of these is going to match up? So the question is, what's the difference? This one goes from 0 to 8, so it's 9 subdivisions, but starts at 0. This one's 1 to 9. It's also 9. So they're both 9 rectangles. But where do you start at? And I would say for this one, since you're looking at the rectangles, they actually start at 1. Or the height's based off of the right side. So you kind of have to look at, like, the height's based off of, like, the first one's not going to be based at 1. It's going to be based at, like, 1 2/3. I think it's going to be C. And there it is. Because if you base it off, like, the starting point, it would have been 0. Okay, that's kind of weird. Let's go to the last part of this. And this is, I think, where it really gets to what SalCon does, or what AP does. They'll say, hey, we want to do Riemann sums with infinite rectangles, because the limit as you go to infinity, number of rectangles will be equal to the actual integral, right? So it's like the Riemann sum, or the sigma definition of an integral. I think they get into, so it's like, hey, how do I represent the integral from 2 to 6 of this function with sigma notation? And it's an infinite number of rectangles, right? So I'm not going from 1 to 9 for 9 rectangles. I'm going from 1 to infinity for rectangles. And I think that's where they get with this. So we're going to infinite rectangles, right? But how do I represent that? So is this that same function? 1/5. No. So here's the idea with this kind of stuff. The limit definition is this thing right here. And I think what you really need to understand is, how do I translate this to the integral graph? Right? Oh, I hated what they did something weird here. So, oh, they made it messed up. So here's my rules to figure this one out. The original was supposed to be 1/5. Let's say they rewrote this. We're going to rewrite this one right now. I hate that the 5 is here. That 5 should actually be on the outside. Should be 1/5 right here. So, one point to this. You're always going to have, like, the function part. You know how, like, we had square root of x earlier for that previous problem? And this is going to be like my delta x part. This is the width of every rectangle. So one of the hints, if you're trying to solve this in multiple choice, is this is always going to be like 1 over n. But whatever number's on top is going to be the let's say the span, the length between the upper and lower limits. This is kind of our, I wouldn't say width anymore. Maybe I can call it the width. This is going to be the width of the integral. In the case of this one, we're going from 6 to 2. The width's going to be 4. That's why we have a 4 on top. Boom and boom. Now, the trick here is to always figure out, why is it 4i over n? what was my trick for doing this was like, how do I explain this? Okay. N's going to infinity. I think I always do this, is I go, take this function. And I go, let's say we have this integral of 1 over 5 to the x, right? Go way back up here. I want to figure out the left hand and the right hand points. So my backwards way of doing this, did I lose track? No, it's right here. Is what if so n is always equal to infinity. Let's check it when I equals 1. And then I is equal to n. Because eventually I goes up to n. And n goes to infinity. And this blows my mind. It hurts. So if I was equal to 0, this would be 2 plus 0 squared. So it would be 1/2 times 2 squared. If I was equal to n, and we're talking limits, the I and the n would cancel out. So I'd be, oh, this is not 1/2, this is 1/5. Be 1/5 times 2 plus 4 squared, so 6 squared. Notice how our limits go from 2 to 6. That goes from 2 to 6. Now, if you're really confused by that, so was I. Let's do some examples. Oh, man. This is why I don't actually have a lesson for this. Okay, so let's look at this. This is a very typical AP problem. Which one of these matches up? So here's my first thing I check. I was doing this. I go 0 to 3. And I go, my length has to be 3. So my length right here has to be 3. So that and so I'm looking for a 3 over n for the thing they're multiplying by. So I'm going to look at this and go, uh-huh. Nope. Nope. Now, I want to figure out, so it's e over 2I to the n or 3I over n. So I know I have to go from 0 to 3. So I'm going to plug the first one in when I is equal to 1. Because that's going to be like the left-hand side. And then try it when I equals n. Or just this formula part. So for this one right here, you plug in I equals 1. I would get e to the 0. And then I equals n, I'm going to get e to the 2. Because the n over n will cancel. For this one, I'm going to get e to the 0. That's e to the 3rd. Now, when you're looking at your actual integration, this goes from e to the 0 to e to the 3rd. So my answer is D. That matches up. And let's see. Oh, I'm right. Try another one. Stealing from Salcon. Maybe he explains this better. Let's try this one. All right. So I'm going from 1 to e. So I know my length is e minus 1. So it's like 1 point. Since it's rational numbers or irrational numbers with e, I'm just going to say e minus 1. So I'm looking for an e minus 1 over n. Nope. Nope. Now, if I'm checking my limits on left and right, so the left one's going to be ln of 1, and the other side's going to be ln of e. So when you're plugging in I equals 0, I equals n. I think it's 0 to n. Yeah, that's what we're going with. Gosh, I think it's 0 to n. So if you plugged in 0, what would you get? Is it really 0? It's supposed to be like, No, it's 0. Oh, 0. If I plug in 0, I get 0 here. Hot 0. It's oh wait, it hasn't been 0. It's been 1. Because we start at 1 when we do that counting. 1 to n. Yeah. So, but here's the thing. It's technically starting with 1. Let's just do this side first. Well, when I is equal to n, what happens? This one will go to ln of the e minus 1. This one will do ln the 1 plus e minus 1, which is ln to the e. So it's b. Done. Okay. Now try Khan Academy.